Thank you very much. So I'm Mary, and I'm a philosopher, and I'm interested really in the question of what is a number. So in philosophy, we're full of questions, probably a lot more questions than answers, I think. And if there's anything like a methodology in philosophy, a driving force in philosophy, it is really the maxim to question everything. But can we really question everything, really? Think about the things you're most certain of. Does it, of course, any of us, like young children, can just keep asking why, but at some point we might think it's no longer reasonable to do so. So of the things that we're most certain about, we might think there really is no point in setting up whole academic departments to question those things. So we might think, we're all pretty sure that we're here now. Is that something we should question? And if you try and think of the things that strike you as most certain, probably the statements of standard basic arithmetic that you learnt early on at school strike you, I hope, as the kinds of things that we really shouldn't be bothering about questioning. Can we really question whether 2 + 2 = 4? It's just so basic. And it's certainly very familiar to us all, right? We all use this claim all the time. 2 apples and 2 more apples make 4 apples. 2 oranges and 2 more oranges make 4 oranges. 2 rabbits and 2 more rabbits. Well, maybe not, but that was a cheap shot, right? That's a cheap shot. Because what we really mean by 2 + 2 = 4 is once you've got the right kinds of things to count, the kinds of things that don't multiply when you put them together, or perhaps the kind of things that when you put them together, they don't merge together like raindrops. Once you've got the right kinds of things, countable things, if you have any 2 of them and any 2 others of them, you're going to end up with 4 of them. So we mean something like this, right, where the blobs are the kinds of things that don't behave like rabbits or raindrops or all those awkward customers. And if we restrict ourselves like that, we might think, look, there's just no way we could go about questioning a claim like that. It's just kind of obvious. What else could it be, 2 + 2 = 4? And there's a sense in which I'm going to say that's right, actually. I'm not going to question the claim. If we understand this claim as saying, look, if you've got any 2 things, countable things, not rabbits, not raindrops, you've got any 2 of the right kinds of things and any 2 more of the right kind of thing, and put them together, you're going to end up with 4 things. That general claim about what happens when we're counting things when they're the right kinds of things to be counted that don't multiply seems to be pretty hard to question. People might question it, but I'm not questioning it here. So if all that we meant by 2 + 2 = 4 was any 2 things and any 2 other things give you 4 things, then I'd be reasonably happy with that. But as a claim of mathematics, 2 + 2 = 4 doesn't say that, or doesn't just say that. Because when we write this claim down, we use these terms, the numbers, 2 and 4, and we use them in a way in mathematics that is more than just an abbreviation for a general claim. So we could just say, oh, look, this is just a shorthand way of writing any 2 things, and any 2 more things give you 4 things, fine. But in mathematics, actually, when we write 2 + 2 = 4 like that, we're doing something a little bit different, because it's a consequence of this claim in mathematics that there is an object, namely the number 2, which added to itself makes 4. And there's lots of true things we can say in mathematics about that object. We can say it's even, we can say it's prime, we can say it's unique. In fact, it's a unique even prime number. So in mathematics, we use 2 + 2 = 4 as more than just an abbreviation for a claim about what happens when we do some counting of stuff. We use it as a claim about the numbers, these objects, the number 2, the number 4, and their relations between each other. And mathematics includes all kinds of theorems about these objects. And this leads to the question that concerns me, which is really, what kind of things are they? What is it? What is the number 2? We don't just sort of bump into the number 2 in the street. It's not that kind of thing. It's not spatiotemporal. And so one major philosophical question about mathematics is, well, what are these objects that are kind of different from the, I couldn't have brought the number 2 and put it on a table out there like all the other objects people have brought along today. Well, I'm going to let you in on a secret. In philosophy, actually, nobody really knows what the number 2 is. But that's not to say we know nothing. We've got very good reasons to say lots of things about what the number 2 is not. Right? So, as I said, it's not physical. It's not something that's walking about. It's not there in the concrete world. Similarly, it doesn't seem to be temporal. So the facts about the number 2 don't seem to depend on when you say them. 2 dinosaurs and 2 dinosaurs always made 4. It doesn't seem to be mental either. So it's a theorem of mathematics that there is a unique number 2, but that unique number 2 doesn't exist in my mind or yours or any of ours. It doesn't seem to be linguistic. The truths about the number 2 in mathematics transcend what we can say about them. And it's not merely symbolic. So there's lots of facts about the symbol 2. Here's an example of one that's been drawn with legs and so on. But the facts about the number 2 in mathematics are different from the facts about the numerals that we use to express those things. So we've got lots and lots of reasons for saying that the number 2 is not any of these things. But our problem is we don't really have anything positive to say about what it is. We do have a word. So with all of our many years of thinking about this, philosophers have come up with a label for this. So we say number 2 is an abstract object. But that doesn't really solve our problem of what it is. Because when you ask, well, what's an abstract object, people say, well, they're not spatiotemporal, they're not mental, they're not linguistic, they're not symbolic, they're something else. And that entirely negative characterization still leaves open the question, well, what positive can we say about these things? And this really leads to a central problem, because if we can't say anything positive about what the number 2 is, it's really hard to say anything about how we can know things about the number 2. So once we've got, an account of physical objects, we can give an account of how we can know things about physical objects through interaction with them, or mental objects through introspection and so on. But if they're not physical or not mental or not any of these other things, it's really hard to say anything positive about how we can know things about these abstract objects, which leaves us in trouble, I think, because we started out thinking, well, 2 + 2 = 4 is one of those things that is most obvious. It's the most certain thing in the world. And now we're in a situation where, well, we don't really know what the 2 is. We can't say anything, what number 2 is. We can't say anything positive about it. And without that positive story, it's really hard to say how we could know anything about the number 2. So do we really know even those very basic things like 2 + 2 = 4? So that's the puzzle. And I'm going to offer you a solution that comes from an unlikely place. Because the solution comes from thinking, the number 2 is just like Sherlock Holmes. Well, what do I mean by that? Well, we know lots of things about Sherlock Holmes, right? He's a detective, lives in Baker Street, mates with Watson, good at solving crimes, bit of a drug problem. We know all these things about Sherlock Holmes. And we know them because they're in the Holmes stories, right? We know them because Conan Doyle told us them. But on the other hand, there's a sense in which we don't really know anything about Sherlock Holmes at all, right? Because there is no Sherlock Holmes. There wasn't a detective who lived in 221B Baker Street. He didn't have a mate called Holmes because he wasn't a person at all. He's just a fictional character. So if I started puzzling about how do I know all these things about Sherlock Holmes, and ask the question, well, what kind of object is Holmes? How do I interact with him? And so on. They hopefully strike us as kind of silly questions because we know all the things about Sherlock Holmes just because they're true in the Holmes stories. And what makes them true in the Holmes stories is Conan Doyle said so, right? So they're true about Holmes because they're in the Holmes stories or they're consequences of things that Conan Doyle told us in the stories. And there's lots of interesting questions in literature about how much we can read into the content of a story beyond what's said there, but certainly I think most of us think, even if Conan Doyle never said it, it's true that Holmes ate and breathed and couldn't fly when he flapped his arms and so on. These are consequences of, the story, even though they're not explicitly said. So there's lots of things that are true about Holmes. True about Holmes because Conan Doyle said they were, or because they kind of follow from things that Conan Doyle said. And that's the case, even though in another perfectly sensible sense, nothing really is true about Holmes at all, or none of those standard things are true about Holmes at all. There is no Sherlock Holmes, right? So there's nothing for those claims to be true about. So I want to say, well, the number 2 is kind of like Sherlock Holmes in this regard, right? In that there are lots of things that are true of the number 2, not because there is this object, the number 2, that these claims are true of. The sense in which they're true about the number 2 is because they're true in the story of standard arithmetic. So we have this story of standard arithmetic that tells us that there are these objects and numbers, 0, 1, 2, 3, and so on, and they satisfy certain assumptions. And once we've set that going, it kind of follows from those assumptions that 2 plus 2 equals 4. Okay. And that's the case regardless of whether there really are numbers, or regardless of whether there even could be such things as numbers. We don't even know what it would be for there to be a number 2. Nevertheless, we have this story about what the numbers look like. And it follows in that story that 2 plus 2 equals 4. So 2 plus 2 equals 4 is true in the story of arithmetic, just like Holmes was a detective, is true in the Holmes stories. Now, we might think, well, what is this story? There it is. So this is the book of arithmetic. Dedekind's Nature and Meaning of Numbers writes down the axioms for number theory, tells you what's true in the story of numbers. A little bit unlike the Holmes stories, we have to think of Dedekind as formulating, retelling a classic story that's been with us kind of as long as we've been thinking about this stuff. But Dedekind formulates this in axioms, and what's true in the story of arithmetic is what follows from those axioms in that story. So, in that sense, then we can say, does 2 plus 2 equals 4? Well, yes and no, right? Yes, in the sense that it's true in the story of arithmetic that 2 plus 2 equals 4. But is it really the case that 2 plus 2 equals 4? Is there really this number which, when added to itself, makes 4? I don't know. I don't even know what that would mean. But for the purposes of maths, it really doesn't matter. And so in this sense, I guess Bertrand Russell is vindicated by something that he said, but now then changed his mind over. Mathematics may be defined as a subject in which we never know what we're talking about, nor whether what we're saying is true. Thank you.
Thanks very much, Mary. I wanted to ask where this leaves numbers like pi, where we seem to still be finding out what's true in the story of pi, and can even be wrong about what happens next in the story. Who gets to write that one?
So, very good question. So the reason why we get pi is through thinking about ratios as extra diameters, and it's true that, so I guess what part of what you're saying is that when we look at the story of pi, it's not that we've written down the full expansion of pi, right? Nevertheless, what the correct expansion of pi is follows from the story we tell at the beginning about what kind of real number it is, right? So there are, even though no one can ever expand it forever because it's got an infinite non-repeating expansion, nevertheless, the facts about what the next step is at each point are all consequences of the basics that we get from the definition of real number, and then the account of where pi fits into those real numbers as a ratio of the diameter of the circle to its circumference. So it's a really nice example in which our mathematical stories go beyond what we as authors kind of put into them, right? Because we can start with quite quite simple basic axioms and definitions. And actually what logic gets to churn out of those is goes far, far beyond anything that that we might have built into it, and defies our expectations, and that's kind of what makes maths hard and interesting and fun and so
on. Mary, thanks ever so much. It just occurs to me that you might have said this, but didn't quite say that Conan Doyle is, rather Sherlock Holmes is an imaginary detective, not a real detective. What does what you're saying do to your advisory nomenclature for all our numbers? In fact, of course, 2 and 2, they aren't even real, they're natural numbers.
Yeah.
Let me push the last question onto the complex plane. Where on earth does this leave what we now call imaginary numbers?
Yeah,
Are they doubly imaginary?
Yeah, they're all imaginary, the lot of them. So I guess when the complexes were introduced, they got the special name imaginary as it kind of struck people at that point. We're kind of making this up now, right? We need something here to do this job. Oh, let's just write in a new character, throw it in, and there we have I, and then off we go again. Whereas the natural numbers and the real numbers, the rational numbers, they've all been so long a part of our intellectual history that it's hard to think of those as our creations, right? And there's a sense, well, I guess, yeah. So there's a sense in which they are, and a sense in which they're not our creations, right? So there's a sense in which if you start with the counting numbers, 0, 1, 2, 3. Well, I talked at the beginning about the very close relation of the mathematical claim 2 + 2 = 4 to just a basically true general claim, any two things and any two things make four things, right? So there's a sense in which the natural numbers really are very natural as an invention, but as an invention for, we're going to abstract from something that just really is a bunch of facts out there in the world, right? So we introduce this system of the numbers to sort of capture the general form of certain relations between just true claims about counting and numerosities. I still want to say, well, at that point when we did that, we introduced something that was an invention, a very useful one, but it's got this naturalness because of its close relation to this practice of counting things. You know, when we're trying to keep track of. So I'm going to diverge a bit and talk a little bit about the history of maths that I know of. So years ago, I attended a course that Eleanor Robson was giving, who does Babylonian mathematics, about the development of Babylonian maths, and it's really stuck in my head how the Babylonian numerals came about, right? So what they used to do, they'd be trading sheep and stuff, and to keep track of their trades, they would make a little box and put beads in the box to represent, okay, you know, 30 sheep or whatever. They'd match and put up the beads with and then they'd put the beads in the box, and then they'd have to sort of seal the box so that then no one could take the beads out or whatever. And they sealed the box and off they went. And after a while, they got annoyed that every time they came back to do their trades, they had to smash the box, right, to find out what was in there. So they realized that when they sealed the box, they could also just put these marks on the top of the box corresponding to each of the beads that went in. So they had their 30 beads in the box, and then they had their 30 lines on the thing. So they did that for a while, and then they realized, well, now what we're doing is we're looking at these boxes with all these beads in, but we don't need to do that anymore, right? We've got these these symbols. So that's how. So the Babylonians use these sort of strokes and then abbreviations for those and so on. And it's a really natural move from, okay, we need to keep track of these trades that we're doing, to we need a symbolic language to do that, to let's just treat these things as the things we're dealing with now, the numbers, rather than the things that they represent. And that sort of, it's natural, but it's still created by us, I want to say.